4.4 is evaluating logarithms and the change of base formula. Just as a reminder, the common logarithm is log base 10 of x. When we're in log base 10, we don't have to write the base. We can just write log of x, and it's understood to be base 10 when there's nothing written there. Find each value, round to 4 decimal places when necessary. For this example, we have the log of 10 to the 7th. It helps if you write it in there if you're uncertain about this. It's log base 10 of 10 to the 7th. So that means what exponent would I put on 10 to make it 10 to the 7th? The answer is 7. Log base 10 of 0.01. It helps when you're evaluating this if you say the decimal in a different way. Instead of reading it as 0.01, you can read it as 1/100th. So what exponent would you put on 10 to make it 1/100th? Well, to make it a 100, you would put a 2 on there, but if you would make it a -2, then it flips it, makes it a 1/100th. Log of 643 divided by 287. This is not something that's in base, these numbers are not in base 10, so you'll want to get your calculator and do that. So we have the log here, log of 643 divided by 287, and that is approximately 0.3503. Now if I had the log of 643 minus log of 287, go ahead and write that in, put that in there, log of 643 minus the log of 287, and there you go. You get the same result as the last time. And that's because our log properties say if you have the same base log and the logs are being subtracted, you can write it as a single log and divide the arguments, with the negative log argument being on the denominator. So this is the same as our previous answer. This is an application of the a model with using common logs, and it's for pH, used in chemistry all the time. So your pH is equal to the negative log of the hydronium ion concentration in moles per liter. Just a note, you will not have to have this formula memorized. This is simply a place where logarithms are used. So if this were to be given to you as a quiz problem or a test problem, we would give you that formula and tell you what it means, and then using it would be the work that you would do. Example 1, we need to find the pH of a lime where the hydronium ion concentration is 1.6 times 10 to the -2. So the pH is what we're finding. It's equal to the negative log of the hydronium ion concentration being 1.6 times 10 to the -2. So we can just put that directly into the calculator. Negative log of 1.6 times 10 to the -2, and close your argument for your log, and we get a pH of about 1.8. So 1.8, and that concentration again is in moles per liter. We want to find the hydronium ion concentration for drinking water if it has a pH of 6.5. So we'll put a 6.5 in for pH for the formula, and that equals the negative log of the hydronium ion concentration. Okay, so here we are in base 10, of course, and we need to solve for the argument. So we're going to change this using the definition for logs. We're going to change it into exponential form. The first thing that we need to do though is isolate the log. We need to get rid of this negative. So it's going to be a negative 1 that we multiply both sides by to get the log by itself. And then we change to exponential form. So it's 10 to the negative 6.5 equals H3O positive. And then you can use your calculator. 10 to the negative 6.5, and that's going to be 3.16 times 10 to the negative 7. So your hydronium ion concentration is equal to 3.16 times 10 to the negative 7. Make sure and read that correctly off of your calculator there. Natural log, just a reminder for you, when we have something that's log base e of x, then the natural log is what we use. This means the same thing as log base e of x. It's just so commonly used, it gets its own notation with the natural log of x. To find these values, we can use our definition. Remember, this is base e, so the natural log of base e of e to the 5.8. In other words, what exponent do I put on e to make it e to the 5.8? That's going to be 5.8. What exponent do I put on e to make it 1 over e to the 4? And that would be a negative 4, causing that to go to the denominator. Here, you don't have an e in the 39, so you're going to use your calculator. Natural log of 39, and we get about 3.6636. Another application of logarithms is decibels, how intense a sound is. Just to note, you do not have to memorize this formula. It's an application that we're using here to show you where these logarithms are used. If you were to be given a problem like this for a quiz or a test, we would give you the formula, tell you what the things mean and what they represent, but it'd be up to you to show the work on how to use the formula. Here we're supposed to find the decibel ratings of the following sounds with the given intensities. Well, your loudness is measured in decibels. We first assign an intensity of I sub O to a very faint threshold sound. If a particular sound has intensity I, then the decibel rating D of this louder sound is given by this formula. Decibels is 10 times the log of I over I sub O. So here we have a whisper is 115 times the intensity of the threshold sound. So to find your decibels, it is 10 times the log of the intensity of a whisper divided by the threshold sound. Of course, your I sub O's will cancel, so the decibel is going to be 10 times the log of 115, and we put that into the calculator. 10 times the log of 115. and we get 20, 21. So D is about, your decibel is about 21 decibels. A busy street is 9,500,000 times the intensity of the threshold sound. So to find the decibels, that's going to be 10 times the log of 9,500,000 times the intensity of the threshold sound, and divide that by the intensity of the threshold sound. So it's simply 10 times the log of 9,500,000. So 10 times the log of 9,500,000, and there we get about 70, about 70 decibels. And our last one is a jetliner at takeoff, and that is a large number. We're talking, this is thousands, millions, billions, trillions, so it's 109 trillion times the threshold sound. So our decibel will be 10 times the log of 109 trillion times the intensity of the threshold sound divided by the intensity of the threshold sound. So we have 10 times the log of 109 trillion, and so that's 10 times the log of 109 . There you go. And we get about 140 decibels. No doubt a very loud sound. In modeling domestic leisure travel, we have this bar graph showing the number of leisure trips within the United States in millions of person trips of 50 or more miles one way over the years 2009 to 2014. This function of t, which is 1458 plus 95.42 natural log of t, with t being greater than or equal to 1, t represents the number of years since 2008, and f of t is the number of person trips in millions, approximates the curve reasonably well. So we want to use this function to approximate the number of person trips in 2012 to the nearest million. And how does that approximation compare to the actual number of 1,588 million of those person trips of 50 or more miles one way? So let's go ahead and try this. If our t is the number of years since 2008, and we're talking about 2012, then our t is going to be 4. Okay, so we're taking f of 4, and that's 1458 plus 95.42 times the natural log of 4. And we'll put that into the calculator. 1458 times, plus 95.42 times the natural log of 4, and that model gives you about 1,590 trips. And we're off just by a small number, just 2 million trips. So if you're looking for something to model it, I'd say that that's a pretty good model, even though you're off by quite a bit, really. But your change of base theorem says that for any positive real numbers x, a, and b, where a does not equal 1 and b does not equal 1, the following holds. The log base a of x is equal to the log base b of x divided by the log base b of a. To prove this, one thing that you could do would be to say that the log base a of x equals y and find another representation for y. So we could rewrite this in exponential form, a to the y equals x, and then we can use the log as an operator. I'm going to take a log base b of a to the y, which is going to equal the log base b of x. Our power property says that we can take this y, that is the exponent on the argument, and bring it in front of the log to be the coefficient of the log. So this is now y times the log base b of a, which equals the log base b of x. And now we're going to divide both sides by log base b of a. So that's going to be log base b of x divided by the log base b of a. And now if y is equal to the log base a of x and y is also equal to the log base b of x divided by the log base b of a, then that must mean that the log base a of x equals the log base b of x divided by the log base b of a. So let's see where this comes in handy for us. We're going to use the change of base theorem to find an approximation to 4 decimal places for each logarithm. So this is, according to the change of base theorem, we could write this as some log base b of 9. Why don't we use base 10 since we have base 10 in our calculator? So we'll make this a log base 10 of 9, and this a log base 10 of 2, and then we'll divide that. So log of 9 divided by log of 2, and we get about 3 let's see, how many decimal places did we say? 4 decimal places, 3.1699. And here we have the log base 1/3 of 2. I could do the same thing, or let's say if I wanted to do it with natural log, I could write this as the natural log of 2 divided by the natural log of 1/3. And then when we put that into the calculator, it is the natural log of 2 divided by the natural log of 1/3. And we get about negative 0.6309. All right, and log base 0.91 of 8. So we do the same thing. Again, it doesn't matter if you use log or natural log. You could use another log if you wanted as well. We're just sticking with log base 10 or log base e since we have that in the calculator. But this will be the log of 8 divided by the log of 0.91 if you want to put it into base 10. So I have the log of 8 divided by the log of 0.91, and we get a negative 22.0488. All right, just as a demonstration, we can go back up to this one. Say that we decided instead of doing natural log that we wanted to do the log base 10. So we can do log of 2 divided by the log of 1/3. and that comes out exactly the same as if we did it with natural log. And on the TI-84 calculators and some other calculators, you also have log base. So you can go here to your math button, and under that math menu, scroll up so that you're going up from the bottom of the list because it's there towards the bottom of the list. You could do log base and it will give you this template. So you could say, go back up to the first one, log base 2 of 9, and it's going to calculate the same thing as if you had done it with the change of base theorem. If you don't have that button, then you're going to use the change of base theorem instead of the button. That number that you're calculating is the exponent that you put on 2 in order to turn that into 9. So you can try that out. 2 to an exponent of, go up and grab that number, and you get pretty darn close to 9. There are some round off factors in the calculator there. Let's evaluate these logs. We have f of x equals 3 the x, and we want to find f of log base 3 of 2. So if I have that, I have 3 of exponent of log base 3 of 2. Our properties that we learned in the last section means that that's going to give us an outcome of 2. When you have a logarithmic exponent with the base the same as the base here, then the answer is going to be the argument of your log. And here we have f of log base 3 of natural log of 3. So this is 3 to the x, but my new x is log base 3 of natural log of 3. Okay, again we have the same base here, so the answer is going to be the argument of our argument of our exponent there. So I get the natural log of 3. That's an exact answer. And again, if we did this, we'd have 3 to the log base 3 of 2 natural log of 3. Bases are the same again. So the answer is the argument of your logarithmic exponent. Given f of x equals the log base 2 of x, we want to find f of 2 to the 7th. So this is going to be log base 2 of 2 to the 7th. So we're being asked what exponent do you put on 2 to make it 2 to the 7th. That's going to be 7. Here I have the log base 2 of 2 to the log base 2 of 2. We have that exponent rule that says, that power rule that says the exponent on your argument can come out in front and be the coefficient of the log. So that would be the log base 2 of 2 times the log base 2 of 2. And so now I can see, well, the log base 2 of 2 is 1. The log base 2 of 2 is 1. So that's going to be 1 times 1, which is 1. This last one, part C, I have the log base 2 of 2 to the 2 log base 2 of 2. And again, we can use our power rule to make that exponent of 2 log base 2 of 2 come out in front and be the exponent of log base 2 of 2. Log base 2 of 2 is 1 times 2 is 2, and we're multiplying that by log base 2 of 2, which is 1, so I get 2. And just a caution here, because students do tend to get this property mixed up with the change of base formula. Remember that the log base 15, remember that the log of 15 minus the log of 28 can be written as the log of 15 over 28. The property says you can write the log one time and divide the argument. So that's how we do that. This is not the same as log of 15 over log of 28. And you can put that into your calculator to see that. Log of 15 over 28 is a negative 0.2711, and that is not equal to the log of 15 divided by the log of 28. So that is not equal to 0.8127, not at all equal. This comes from, if you wanted to, you could rewrite this as the log base 28 of 15. So it's the log of the original argument divided by the log of the original base. That's change of base formula. This is your quotient property. So do not confuse those two. Those are not equivalent. That finishes up your lesson for 4.4. Go ahead and start on your homework and let me know if you have any questions.